As we begin our study of universal gravity in the solar system, it might be interesting to start by just asking ourselves what it is that enables a satellite to stay in orbit. So if someone asks you that, would you have a ready response? In other words, what keeps it moving? And then why doesn't it just fly away? And why doesn't it crash into the Earth, say, if we're talking about the Earth? So some quick answers to that may go something like follows. What keeps it moving? You really ought to know what that is. An object in motion wants to stay in motion, doesn't it? Unless acted on by a net unbalanced force. And therefore, what keeps it moving is inertia. Once it's moving, it wants to stay moving. Okay, that makes sense. So that keeps it moving. It doesn't need a rocket engine to continue to travel. Okay. Now, why doesn't it fly away then? In other words, it's moving, and it would keep moving in the direction it's going unless something is preventing that. Oh, something is preventing that. And you know what it is. You know what it is, don't you? It starts with a G and ends with T. Gravity, which tugs it inward. Okay, and then, all right, so if gravity's tugging it inward, why doesn't it crash? Gravity's pulling on it, should slam into the Earth, right? Well, it's an interplay of gravity and inertia, really. But let's look at it this way. Earth curves away at the same time. So really, gravity is accelerating it toward the Earth. But while it's doing that, while it's accelerating toward the Earth, it's moving sideways as well, tangentially. And that inward force causes an inward acceleration, but it's moving tangentially at the same time. So as it moves sideways, Earth is curving away, so it all comes together. Well, let's consider the details about Earth in particular. So what we're going to do is see how much Earth curves away per mile. So we're going to consider a 1 mile distance. Think of a platform moving tangent to your position on Earth right now. And here it is, the 1 mile. Well, how much does the Earth curve away? How much does Earth drop if you extend straight out a mile? Now, that'd be a good thing for you to guess right now. Do you think it'd be, I don't know, half a mile? Maybe 100 feet? Maybe an inch? Maybe a nanometer? Probably don't have a very good reference point to know what the answer is. So this is what we're going to determine, this little d right here, given that the radius is 4,000 miles. Obviously, this is not to scale, since 4,000 here and 1 here are very much not to scale. But let's use Pythagorean theorem and let y equal the hypotenuse, the 4,000 plus d. Therefore, d is y minus 4,000. All right. So now we know what d is. Now y is equal to square root of the sum of the squares, 4,000 squared plus 1 squared. And we need to keep all the decimals in here to really get a handle on this, because obviously it'd be tempting to say, well, this approximates to just 4,000, so just leave it like that. But really it's 4,000.000125. So that's a lot of sig figs that we're going to use in our analysis. D is equal to then 4,000.000125 minus 4,000, which is 0.000125 miles. Well, that's a very cumbersome number, so let's convert it to feet by dimensional analysis, and then to inches, and we discover that it's 7.92 inches per mile, or right about 8 inches. So that's how much the Earth curves away from us if we extend out 1 mile straight from our position, tangent to the surface of the Earth. Okay, let's look at some basic orbital physics now that we have the canon of physics on the Earth, which is so large that it would sphericize under its own gravity as it plummets into the Earth itself, is subsumed by the Earth, accelerating into it at 9.8 meters per second squared to begin with. Not enough iron on the whole planet to construct that cannon, but nevertheless, we're going to fire a cannonball and consider what happens at various speeds. So that was a little wimpy, a little bit faster, and it still follows some curved path and lands on the Earth somewhere in the distance. Well, these are both examples of something that you have already studied in vertical circular motion, and these particular two examples are examples of too slow speed. But if we continue to increase the speed, if we continue to do that, eventually we'll come to a point where the cannonball actually goes around a circle around the Earth and smacks itself in the tail. And this would be what we have learned as the just right speed, where gravity alone is acting to cause the cannonball to curve and go in a circle in this case. It's the circular speed. And we've studied basic circular motion already anyway, so we know a little bit about what that is as far as equations, distance over time, 2 pi r over t. And in this case, what we have is gravity acting on the cannonball. Here's the radius, there's gravity, that is the force. The nice thing about the analysis of forces in this unit is that we have no support force. The only force acting is gravity. So that's got to be real simple, right? Certainly. So sum of the forces, Fc. So we can say mg, which is the sum of the forces. The sum of the forces is mg, and that's Fc, or mv squared over r. M's go away. Orbital speed is rad rg. So that looks familiar as well. We've encountered that before. And this is really useful for our current concerns. We also could say mg is equal to, well, this is not the only formula we have for centripetal force. M4 pi squared r over t squared is a great little formula as well, especially for our interests now. Because, for instance, how long does it take the satellite to orbit? Notice it tends to always be mass independent. So there it is again. Doesn't matter what the mass is of the object orbiting. So the period is, by a little bit of algebra, 2 pi squared of r over g. Now there's that form again. Remember, for a spring, 2 pi squared of m over k. For a pendulum, 2 pi squared of l over g. Then for a conical pendulum, we had 2 pi squared of y over g. Now we have 2 pi squared of r over g. So it's probably not all that surprising. Okay, let's go yet a little faster. And we come to the most general form for an object in a bound orbit, which is the, I'll call it the too fast speed. It's not really too fast in the sense that it needs some other forces acting on it, like we saw before. Too fast roller coaster loop, you need a support force. There is no support force now, but what happens if we're going a little faster than the just right speed is that the shape gets distorted and it becomes an ellipse. So it's an elliptical path. Technically, what I just said, shape becoming distorted, that's not correct. Elliptical shape is the natural, normal shape. Actually, it turns out that the circle is just a special case of an ellipse. All right. Let's calculate the speed and the period based on the radius of Earth given here, and g being 10 meters per second squared, approximately. And let's convert meters per second to miles per hour and seconds to hours so we can have regular units that we're used to. So v, rad rg. Square root of 6.4 times 10 to the 6 times 10. That gives us 8,000 meters per second. Well, that's cooking along, but do you know what that really is? Let's do dimensional analysis and find out what it is in miles per hour. And there it is, folks. About 18,000 miles an hour. 17.9. That is moving. So that's the speed of an object in circular orbit above the surface of the Earth. Hopefully high enough to scale the tall buildings, the trees, the mountains, but that's obvious. Okay, what about the period? 2 pi squared of r over g, plug in the numbers, and what pops out for us is 50.26 seconds. It's a little cumbersome. 1.39 hours, or just about 1.4 hours. So a little less than an hour and a half it takes an object to circle the Earth. When you see the satellites up in the sky, it takes 1.5 hours for those satellites to make one orbit. Kind of interesting. Freely falling toward the Earth the entire time, being pulled inward by gravitational tug at the just right speed. 1.5 hours to fall toward the Earth and go completely around.